The F-16 pilot's cockpit erupted into chaos as the radar warning blared. A Houthi SA-6 missile traveling at Mach 2.8 was locked onto his aircraft, closing in rapidly over the waters off Yemen. In a tense aerial showdown, the pilot executed a desperate dive, deploying countermeasures and activating electronic warfare systems. This is the gripping tale of how U.S. airmen narrowly escaped a direct attack, setting the stage for a significant military response in the region. Stay tuned as we delve into the behind-the-scenes maneuvers and decisions that shaped this dramatic encounter. The SA-6 threat emerges. The SA-6 gainful missile system posed a significant threat in the Yemeni theater of operations. Originally designed by Soviet engineers in the 1960s, this surface-to-air missile system has been modernized by the Houthis to counter NATO aircraft at medium to high altitudes. These adaptations made it dangerous enough to threaten even advanced U.S. fighters. When the F-16 from the 421st Fighter Squadron detected the launch on its APG-83 AESA radar, the situation quickly escalated. The aircraft was on a routine patrol about 42 kilometers from the Yemeni coast, providing air cover for a U.S. Navy task force. Suddenly, the radar warning receiver activated with urgency. The signature of an SA-6 missile accelerating to Mach 2.8 on an intercept course. The pilot had about 45 seconds to respond. The SA-6's continuous wave radar guidance system posed unique challenges. Unlike infrared homing missiles, the Gainful relied on constant radar illumination from its ground-based control vehicle, allowing mid-course corrections. This made it particularly dangerous against aircraft that failed to break radar contact. Historical engagements like those in the Yom Kippur War showed its effectiveness against unprepared pilots, though success depended on operator skill. Modern avionics provided crucial advantages against this threat. The F-16's ANAPG-83 scalable agile beam radar detected the incoming missile at maximum range, offering critical early warning. Within 2 seconds of the alert, the pilot executed a 15,000-foot dive at 6.5 G-forces while dispensing MJU-7B flares and RR-170 chaff bundles. The onboard electronic warfare management system sequenced countermeasures to maximize survivability. Despite these efforts, the missile maintained radar lock through the initial evasion. Like a predator stalking its prey, the SA-6 adjusted its trajectory to match the F-16's movements. Thermographic analysis confirmed the missile had entered its terminal guidance phase. At this critical juncture, the pilot enabled the AN/ALQ-184 Electronic Countermeasures Pod's aggressive jamming protocols. The system transmitted complex pattern noise across multiple frequency bands, disrupting the SA-6's fire control radar. Electronic warfare specialists later reconstructed key details from the aircraft's mission data recorder. The ALQ-184 executed a textbook radar break lock sequence just 6.3 seconds before the projected missile impact. Jamming signals overwhelmed the SA-6's guidance processor, causing fatal navigation errors. Subsequent telemetry showed the missile spiraling uncontrollably before detonating harmlessly approximately 470 meters behind the escaping F-16. Pilots' split-second decisions. The F-16 pilot faced immediate life-or-death calculations when the missile warning system alerted. With the SA-6 approaching at Mach 2.8, the pilot had less than 20 seconds before potential impact. Standard evasion doctrine dictated immediate maneuvers to disrupt the missile's guidance parameters. The pilot reacted by initiating a dive while pulling 6.5 Gs, a maneuver pushing both aircraft and human limits. This extreme descent altered the missile's predicted intercept course. Initial countermeasures proved insufficient against the persistent threat. The aircraft's AN/ALE-47 countermeasure dispenser released MJU-7/B flares and RR-170 chaff bundles in pre-programmed sequences. These decoys created infrared and radar signatures designed to spoof Soviet-era guidance systems. However, telemetry data later confirmed the missile's guidance computer maintained track on the actual aircraft through the initial countermeasure deployment. The missile's semi-active radar homing guidance proved more resilient than anticipated against basic deception tactics. The pilot then initiated advanced evasion protocols rarely executed outside training simulations. Combining hard turns with rapid throttle adjustments, the F-16 created unpredictable velocity vector changes. These maneuvers exploited the SA-6's limited ability to compensate for sudden lateral and vertical displacement. The pilot simultaneously activated the aircraft's AN/ALQ-184V electronic warfare pod in its most aggressive jamming mode. This system transmitted specifically tailored radar noise patterns to overwhelm Serbian original Kvant fire control radar frequencies. Electronic warfare specialists later analyzed the engagement timeline with exceptional precision. At 6.3 seconds before projected intercept, the ALQ-184 successfully induced critical angle tracking errors exceeding 12 degrees. The jamming signals disrupted the missile's Doppler processing algorithms, causing its guidance system to lose valid radar return discrimination between the aircraft and chaff cloud. Flight data recorders captured the exact moment when the missile ceased effective terminal guidance, 4.7 seconds before nearest approach. Final evasion occurred barely beyond the SA-6's lethal radius. The missile passed 470 meters behind the F-16 before its proximity fuse detonated the 59-kilogram warhead. Post-mission analysis confirmed the warhead's radar-activated fuse had attempted initiation but failed to achieve optimal detonation geometry. Shrapnel patterns indicated the explosion occurred at an oblique angle relative to the escaping aircraft, with no fragments striking the airframe. The pilot's execution of complex survival protocols demonstrated exceptional aircrew coordination. Simultaneous management of aircraft energy states, countermeasure deployment, and electronic warfare settings required flawless systems knowledge. Every maneuver precisely followed USAF Fighter Weapons School doctrine for defeating semi-active radar missiles, procedures refined through decades of operational experience against legacy Soviet systems. Key factors in the successful evasion included the APG-83 radar's early detection capability and the pilot's immediate diagnosis of the missile type. Recognition of the SA-6's distinctive launch signature allowed adoption of optimized defensive measures from the engagement's outset. The pilot's rapid identification of the missile's guidance phase transitions enabled precisely timed countermeasure employment. MQ-9 Reaper under fire. An MQ-9 Reaper conducting surveillance near Hodeidah became the next target of Houthi air defenses just 17 minutes after the F-16 engagement. The unmanned aircraft's radar detected the SA-6 launch at 42 kilometers, triggering its missile warning system. Unlike the F-16, the Reaper's slower speed of 240 knots made it more vulnerable. The ground control team quickly took manual control to evade the threat. The remote pilots executed an emergency climb to 15,000 feet, taking advantage of the SA-6's reduced performance at higher altitudes. This maneuver burned significant fuel, but increased the missile's flight time by 22%. The Reaper's countermeasure system deployed flares and chaff in a sequence designed to confuse radar-guided threats. Its electronic warfare suite also jammed the radar's frequency bands. Despite these efforts, the SA-6 maintained partial track. Telemetry showed the missile's guidance system experienced intermittent lock, but kept adjusting its path. The Reaper's slower speed and larger radar cross-section compared to the F-16 made complete evasion unlikely. At 3.2 kilometers from impact, the missile's proximity fuse detonated the warhead 180 meters from the drone. Shrapnel from the explosion hit the Reaper's right wing, damaging a hardpoint and severing 2 fuel lines. The aircraft's monitoring system detected the damage, and autonomous controls adjusted to maintain stable flight. The composite structure of the wing contained the damage, preventing catastrophic failure. The drone's diagnostics confirmed all primary systems remained operational. The right wing's missile rail was destroyed, but other weapon stations and sensors were intact. Fuel loss triggered automatic transfer protocols, keeping the engine running with minimal performance loss. The Reaper continued its mission for another 37 minutes before returning. Post-flight inspection revealed the damage: 12 shrapnel penetrations, with the largest creating a 14-centimeter hole in the fuel cell. The aircraft's redundant systems design prevented any single failure from compromising the mission. Maintenance crews replaced the damaged wing section within 72 hours, returning the drone to service. This engagement highlighted the vulnerabilities of unmanned systems compared to manned aircraft. While the Reaper lacked the F-16's speed and agility, its resilience and autonomous recovery capabilities were crucial. The incident also exposed limitations in current countermeasures against upgraded systems. Future missions were adjusted to maintain higher altitudes near known SA-6 positions, emphasizing the need for strategic planning in contested airspace. Navy's rapid response. The USS Spruance DDG-111 received orders to neutralize the SA-6 battery within 43 minutes of the MQ-9 engagement. The Arleigh-Burt-class destroyer advanced to a firing position 85 nautical miles off the Yemeni coast, closing the distance to ensure weapons effectiveness. The mobile SA-6 system was a time-sensitive target. Satellite imagery confirmed the Transporter Erector Launcher, TEL, had already departed its initial firing position. Navy analysts predicted the battery would relocate to one of 3 pre-surveyed hide sites within the Houthi-controlled zone near Houthi. Task Force commanders selected the RIM 174 Standard Missile 6, BISM-6, for the engagement, leveraging its dual capability against surface targets. With a maximum speed of Mach 3.5 and a range exceeding 240 kilometers, the missile could reach the target area before the launcher achieved concealment. The SM-6's advanced guidance system provided the critical advantage by homing in on the SA-6 battery's radar emissions during relocation. The Spruance's AN/SPY-1DV radar detected the SA-6's 9S-35 straight flush acquisition radar, transitioning to standby mode at 14:37 local time. This electronic fingerprint allowed precise triangulation of the mobile unit's position. Fire control solutions were computed within 90 seconds, while the missile's active seeker head was programmed for terminal phase target acquisition. The SM-6's onboard systems could discriminate between decoy vehicles and the actual launcher by analyzing radar emission characteristics. Launch occurred at 14:41 from the Spruance's forward Mark 41 vertical launch system. The SM-6 executed its boost phase before transitioning to mid-course guidance from the ship's Aegis combat system. During the 127-second flight, the missile's active seeker detected and locked onto the SA-6 battery's intermittent radar emissions. Terminal guidance autonomously adjusted the intercept trajectory as the Houthi vehicle attempted evasive maneuvers along a coastal road. Impact occurred with a 3.2-meter circular error probability, directly destroying the SA-6 TL and its accompanying 1S-91 long-track radar vehicle. The 140-pound blast fragmentation warhead detonated at optimal height to maximize damage. Overhead ISR platforms confirmed the complete destruction of the missile system through thermal signatures and battle damage assessment imagery. Secondary explosions from the launcher's remaining missiles validated the kill. This rapid naval strike demonstrated tactical innovations in naval warfare, marking only the 3rd confirmed combat use of the SM-6 in surface attack mode. The engagement proved the viability of using naval air defense assets for offensive strikes against time-sensitive land targets. The entire decision to impact sequence lasted just 19 minutes, shifting operational momentum. Electronic surveillance revealed immediate Houthi communications, attempting to ascertain the strike's origin. The lack of aircraft sightings confused rebel forces initially. The SM-6's sea launch provided no visible warning. Post-strike analysis confirmed the destroyed SA-6 battery was part of the Houthis' elite 351st Air Defense Brigade, degrading approximately 17% of their remaining high-altitude air defense capacity in western Yemen. The Spruance's successful engagement validated the Navy's distributed lethality concept in contested environments. Without risking manned aircraft or exposing the ship to coastal defenses, the destroyer executed a precise strike at strategic range. This tactical victory came at minimal cost. A single SM-6 expended from the ship's 96-cell VLS inventory, large-scale retaliation. The U.S. response escalated rapidly following the SM-6 engagement, with CENTCOM planners approving a comprehensive strike package within 6 hours. Fighters from the USS Harry S. Truman's carrier Air Wing 1 formed the primary attack element. 4 FA-18F, Super Hornets from VFA 211, armed with AGM-154C joint standoff weapons, launched first, followed by electronic warfare support from EA-18G Growlers. The Houthis had anticipated retaliation and dispersed their missile stockpiles to hardened sites across 3 governorates, complicating targeting efforts. The JSOW glide bombs addressed this tactical challenge with their imaging infrared terminal guidance and GPS-INS navigation, enabling precise strikes against moving or relocated targets. Their 70-kilometer standoff range allowed launch outside most Yemeni air defense envelopes. Mission planners programmed 14 JSOWs with specialized broach warheads to penetrate underground storage facilities before detonating secondary charges. Primary targets included 3 weapons depots near Saada, constructed with Iranian technical assistance. Satellite imagery revealed these facilities buried under 18 meters of earth and reinforced concrete, rated to withstand direct hits from 2,000-pound bombs. The JSOW's trajectory programming ensured optimal penetration. Post-strike assessments confirmed catastrophic internal explosions, with thermal signatures indicating secondary detonations from stored munitions. As the strike teams prepared for the multi-domain assault, a palpable tension filled the air, underscoring the high stakes of the mission. Concurrent with the airstrikes, the guided missile destroyer USS Gravely executed naval bombardment from the Red Sea, firing 12 BGM-109 Tomahawk Block VI missiles at fixed launch sites along Yemen's western coast. These cruise missiles employed upgraded seekers to discriminate between decoy positions and actual military infrastructure. Targets included hardened revetments for anti-ship ballistic missiles and command nodes coordinating Houthi air defense operations. The combined strikes achieved measurable degradation of Houthi capabilities. Battle damage assessment confirmed the destruction of 14 ballistic missiles, including Iranian-supplied Badr-1 systems, 3 complete SA-6 batteries, and 23 anti-ship cruise missiles. Secondary explosions at multiple sites suggested successful targeting of maintenance facilities and propellant storage areas. Signals intelligence intercepted frantic Houthi communications, attempting to coordinate residual forces and assess losses. The operation demonstrated advancements in U.S. strike methodology. Coordinating simultaneous air and naval attacks required precise timing to overwhelm local defenses. Electronic warfare aircraft maintained constant jamming coverage against known radar frequencies. Strike planners innovated by integrating SM-6 surface attack capability with conventional bombardment, creating layered effects against dispersed targets. Technical analysis revealed notable weapons performance data, with JSOW's infrared seekers successfully discriminating targets despite camouflage attempts. Broach warheads achieved deeper penetration than predicted. Tomahawk modifications allowed in-flight retargeting for 3 missiles when surveillance assets identified relocated equipment. The retaliatory strikes carried strategic implications beyond immediate tactical success. U.S. forces demonstrated willingness to escalate response intensity when challenged, signaling rejection of previous incremental approaches to Houthi provocations. Intelligence monitoring confirmed the strikes disrupted Houthi command continuity for approximately 53 hours, an eternity in operational terms. Rebel forces appeared hesitant to activate remaining air defense systems, fearing additional targeting. Commercial satellite imagery showed unusual movement patterns, suggesting forced dispersal of surviving missile assets to civilian areas. Houthi miscalculation. The Houthi attack on U.S. aircraft was a strategic blunder, akin to a critical slip in a high-stakes chess match, leading to far-reaching consequences. By targeting an F-16 fighter jet, the rebel group crossed a well-established red line, triggering an immediate escalation protocol. The U.S. response was swift, commencing within 6 hours, a testament to advancements in targeting cycles and weapons capabilities that now enable near real-time counterstrikes. Intelligence analysts traced the SA-6 launch to the Houthis elite 351 Air Defense Brigade, a unit trained by Iran's Islamic Revolutionary Guard Corps. This exposed vulnerabilities in their operational security. The missile battery's radar emissions provided precise electronic fingerprints, enabling rapid geolocation. Tracking the mobile launcher's relocation attempts confirmed 3 pre-surveyed hide sites, now part of CENTCOM's target database. The Houthis miscalculated, expecting a measured response based on historical U.S. reactions. However, the Trump administration's 2020 strike against Qasem Soleimani set a new precedent, one the current administration appeared to follow. White House statements emphasized proportional but decisive retaliation, yet the strikes exceeded most analysts' predictions in scope and intensity. The U.S. response marked a shift from reactive to proactive deterrence. Joint Force commanders approved simultaneous strikes against air defense systems, ballistic missile stockpiles, and command infrastructure, target categories previously avoided to prevent escalation. The operation incorporated lessons from Operation Mole Cricket 19, executed with modern precision-guided munitions and real-time ISR integration. Electronic warfare played a crucial role in the Houthi defeat. Rebel communications intercepted during the operation revealed confusion about the SM-6's origins, with many operatives initially blaming Saudi coalition aircraft. The loss of 3 SA-6 batteries represented about 28% of their high-altitude intercept capability in western Yemen. Post-strike satellite imagery showed unusual activity at suspected Iranian warehouses near Al-Hudaydah, suggesting emergency redistribution of assets. Military logistics suffered severe disruption. JSOW strikes against underground bunkers near Sa'ada destroyed an estimated 340 metric tons of stored propellants and 17 assembled missile airframes. These facilities were the Houthis' primary strategic weapons reserve. Rebel attempts to disperse remaining systems to civilian areas exposed missiles to environmental degradation and reduced maintenance capabilities. The aftermath revealed weaknesses in Houthi mobilization. Standard procedures called for immediate retaliatory launches against Saudi Arabia, but none materialized. Signals intelligence indicated paralysis within Houthi command structures, with intercepted communications showing mid-ranking officers requesting guidance on weapons release authority that went unanswered. Iran's reaction was telling. Public statements condemned the U.S. strikes, but private diplomatic channels showed restraint. No immediate resupply shipments were detected through Iranian smuggling routes, suggesting recalculations about the cost-benefit of continued military support amid demonstrated U.S. willingness for a strong response. International reactions. The United Kingdom's Ministry of Defense quickly expressed support for the right of self-defense against unlawful attacks on coalition aircraft, emphasizing the strategic importance of maintaining freedom of navigation in the Red Sea corridor. This signaled potential Royal Navy deployments to reinforce maritime security. France's defense ministry echoed this sentiment, praising the measured precision of American operations while advocating for continued dialogue to prevent regional escalation. Germany's response was more nuanced. Officially, Berlin endorsed the strikes as proportionate under international law, yet privately urged Washington to provide the UN Security Council with detailed post-strike assessments. German intelligence reportedly shared satellite imagery with U.S. counterparts to assist in battle damage evaluations, demonstrating operational cooperation despite public reservations about military solutions. The United Nations reaction highlighted deeper fractures in international consensus. UN Secretary-General Antonio Guterres acknowledged America's inherent right of self-defense under Article 51 of the UN Charter, urging all parties to resist further escalation that could destabilize regional security architectures. Behind closed doors, UN Security Council members clashed over whether to convene emergency consultations, with Russia demanding formal condemnation of the U.S. action. NATO headquarters issued a strong statement condemning Houthi aggression against international air assets and warning of consequences for continued threats to regional stability. The alliance's maritime command announced enhanced aerial patrols over the Bab el-Mandeb Strait, deploying AWACS surveillance aircraft from NATO Air Base Geilenkirchen. This marked the first overt NATO military response to Yemeni developments since the coalition's formation. Middle Eastern reactions followed predictable geopolitical fault lines. Saudi Arabia's foreign ministry praised the strikes as necessary to counter Iranian-backed destabilization, carefully avoiding direct attribution to Tehran. Oman abstained from public comment, but reportedly denied port access to 3 Iranian cargo vessels in the days following the operation. Qatar called for restraint while hosting U.S. Central Command's forward headquarters at Al Udeid Air Base. Israel provided strong regional support through back-channel communications. Mossad officials shared intelligence on Iranian missile shipments to Yemen with CENTCOM planners before the strikes, continuing cooperation during post-operation assessments. The Israeli Defense Forces Northern Command positioned additional Iron Dome batteries along the Lebanese border, anticipating possible Hezbollah retaliation in solidarity with the Houthis. Iran's public rhetoric contrasted with its operational restraint. Supreme Leader Ali Khamenei denounced the strikes as American terrorism, while the IRGC Navy conducted exercises near the Strait of Hormuz. However, no immediate resupply shipments were detected through established smuggling routes into Yemen. Commercial satellite imagery showed unusual inactivity at suspected IRGC warehouses in southern Iran. Asian powers responded with cautious pragmatism. Japan's defense minister confirmed ongoing coordination with U.S. Naval Forces Japan to protect maritime shipping lanes. While China's foreign ministry urged all parties to respect Yemen's sovereignty, Indian Navy commanders unexpectedly diverted 2 Delhi-class destroyers to the Arabian Sea, citing routine exercises. The European Union's External Action Service struggled to formulate a unified position. France and Germany pushed for a balanced statement, while Eastern European members insisted on stronger language supporting Washington. The eventual compromise recognized the legitimacy of defending against armed attack, while expressing profound concern about civilian impacts, reflecting Brussels' perennial divide between Atlanticist and non-aligned factions. Technological edge. The engagement highlighted decisive technological advantages across U.S. military systems. The F-16's radar detected the incoming SA-6 missile at 42 kilometers, providing crucial early warning. This radar's agile beam technology allowed simultaneous missile tracking and situational awareness, a capability Soviet-era systems lacked. Advanced algorithms distinguished the missile's launch plume from ground clutter, preventing false alarms. The SA-6 Gainful posed a credible threat due to Houthi modernization. Technicians upgraded its radar with solid-state components, extending its engagement range. However, its continuous wave illumination made it vulnerable to advanced jamming. The ALQ-184V jamming pod exploited these weaknesses, with adaptive algorithms matching the radar's frequency hops faster than the missile's guidance could adjust. Electronic warfare specialists view the AN/ALQ-184V's performance as exemplary. Its bandwidth management prevented spectrum saturation while maintaining effective jamming. Digital radio frequency memory technology created deceptive radar returns mimicking the F-16's signatures. The pod synchronized noise jamming with chaff deployments, coordinating deception across domains. These capabilities were proven in red flag exercises, showing 87% effectiveness against modernized Soviet technology. MQ-9. Reaper systems showcased different technological strengths. Autonomous damage control minimized shrapnel impact. When sensors detected fuel line breaches, the flight control computer sealed affected sections and rerouted hydraulic pressure. Structural health monitoring adjusted flight parameters to compensate for reduced lift, functioning without human intervention. The Reaper's mission footage provided valuable data on countermeasure effectiveness against upgraded SA-6 systems. High-definition cameras captured the missile's terminal phase, revealing the seeker had initially tracked decoys before reacquiring the drone. This behavior, consistent with Iranian-supplied upgrades, informed updates to countermeasure programming. The SM-6's successful surface strike marked a shift in naval warfare. Originally for missile defense, its processor proved effective against ground targets. The missile's seeker exploited the SA-6 battery's radar emissions during relocation, demonstrating the Navy's any sensor, any shooter concept. Weapons performance data revealed technological milestones. The JSOW's warhead penetrated 22 meters of earth and concrete, exceeding test results. Post-strike imagery showed precise cuts through structures. Tomahawk Block V missiles demonstrated in-flight retargeting, receiving updated coordinates mid-flight. The technological gap is evident in system interoperability. While Houthi forces struggled with battlefield awareness, U.S. systems shared real-time data. The F-16's radar tracking fed into the Navy's network, allowing the SM-6 launch without dedicated targeting aircraft. This network-centric capability remains unmatched by Iran's systems. Human factor. The F-16 pilot faced a classic air defense scenario where technology alone couldn't ensure survival. The ANAPG-83 radar detected the SA-6 missile at 42 kilometers, but the system's warning only provided raw data. Translating that into life-saving maneuvers required human expertise. Recognizing the missile's launch signature as an SA-6 was crucial. The pilot knew this was a radar-guided system needing specific countermeasures. This identification happened in under 3 seconds, faster than any automated system could assess the threat type. Training at Nevada's red flag exercises prepared the pilot for this moment. The 57th Wing's adversary air program simulates engagements against mock SA-6 systems using actual Soviet hardware. Pilots learn to distinguish between original and modernized variants based on radar warning receiver signatures. These exercises drill instinctive responses to specific missile types. When the real alert sounded, the pilot didn't hesitate, initiating a 6.5G dive within 1.2 seconds of the warning while rolling to present the F-16's smallest radar cross-section. The electronic warfare officer monitoring the AN/ALQ-184V pod made critical decisions. As the missile maintained lock through initial countermeasures, the EW officer manually overrode the pod's programming. Instead of cycling through preset jamming profiles, they selected a targeted noise interference pattern, optimized against Cavant radar frequencies. This intervention occurred at 19,000 feet, just 12 seconds before projected impact. Post-mission analysis confirmed the manual selection increased jamming effectiveness by 32% compared to the system's automatic mode. The MQ-9 Reaper operators showed similar adaptability under pressure. When the drone's Pandora system detected the SA-6 launch, standard protocol dictated an autonomous evasion sequence. However, the ground control team recognized this threat required customized tactics. They manually adjusted the Reaper's climb rate to 2,000 feet per minute, 50% faster than programmed responses, while commanding simultaneous flare and chaff deployments. This decision exploited a known vulnerability in upgraded SA-6 seekers that struggle with simultaneous infrared and radar decoys at high climb angles. Both cases highlighted the irreplaceable role of human judgment in warfare's decision loops. The F-16 pilot interpreted subtle changes in the missile's radar illumination patterns during the terminal phase, knowing precisely when to maximize countermeasure effectiveness. Training at Nellis AFB's weapons school instills this skill through realistic scenarios where missile guidance behaviors change unpredictably. Similarly, Reaper operators drew on databases of previous engagements to estimate the SA-6's likely reaction to their maneuvers, knowledge no algorithm yet replicates accurately. The human-machine interface is the heartbeat of the aircraft, reinforcing the indispensable value of trained personnel. Strategic implications: the Houthi attack on U.S. aircraft triggered a fundamental recalibration of military strategy in the region. By targeting an F-16 conducting routine patrols, the rebels crossed a threshold for acceptable provocations. CENTCOM's rapid authorization of retaliatory strikes marked a decisive shift from previous restraint. The overwhelming response demonstrated a renewed willingness to enforce red lines with kinetic action, differing from the measured escalations of earlier administrations. Historical context shaped the operation's strategic calculus. During Obama-era engagements, responses to Houthi missile launches typically involved symbolic strikes against low-value targets. The Trump administration's 2020 Soleimani strike set a precedent for direct action against high-profile threats. This operation blended both approaches, executing precision strikes while eliminating critical infrastructure nodes. Analysts noted the strikes destroyed approximately 40% of the Houthis strategic missile inventory in western Yemen, based on pre-conflict intelligence estimates. The tactical execution carried deliberate strategic messaging. Simultaneous employment of SM-6 surface attacks, JSOW bunker penetrations, and Tomahawk strikes demonstrated multi-domain capabilities tailored to Yemen's complex battle space. This approach forced adversaries to contend with unpredictable response vectors. A warship-launched air defense missile destroying a mobile launcher represented an unconventional tactical innovation with strategic implications. Coupled with electronic warfare suppression, the operation signaled U.S. technological superiority across all warfare domains. Military planners specifically targeted capabilities that maximized deterrent effect without provoking uncontrollable escalation. The strikes avoided Houthi leadership compounds and Iranian advisory facilities, signaling boundaries while demonstrating overwhelming conventional superiority. Intelligence intercepts confirmed rebel commanders initially mistook the SM-6 strike for Saudi coalition action, revealing gaps in situational awareness that U.S. forces exploited. Post-strike assessments showed a 53-hour disruption in Houthi command continuity, an operational paralysis exceeding Pentagon projections. The operation's success carried broader geopolitical ramifications. Saudi Arabia accelerated withdrawals from northern border positions within 72 hours, a move analysts linked to the demonstrated U.S. willingness to independently neutralize threats. Oman's quiet denial of Iranian supply shipments through Salalah port suggested regional actors were reassessing alignment strategies. Even Qatar maintained unbroken U.S. operational support at Al Udeid Air Base throughout the crisis. Long-term strategic effects remain mixed. While the strikes degraded immediate Houthi capabilities, their Iranian backers retained capacity for weapons resupply through established smuggling routes. Commercial satellite imagery captured post-strike activity at suspected IRGC warehouses near Bandar Abbas, though no confirmed shipments materialized within the critical 2-week window. The operation established a clear cost calculus for attacking U.S. assets while leaving Iran face-saving off-ramps to avoid direct confrontation. The Navy's SM-6 engagement established particularly consequential precedents. By successfully employing an air defense missile against surface targets, the Navy validated concepts outlined in its Naval Integrated Fire Control Counter-Air Doctrine. This expanded the tactical toolbox available for responding to time-sensitive threats without committing manned aircraft. Weapons development programs subsequently received increased funding to adapt other missile systems for multi-domain operations, a capability gap competitors currently cannot match. Future threats. The Houthi missile threat remains potent despite significant degradation from U.S. strikes. Intelligence assessments confirm rebel forces retained approximately 60% of their ballistic missile inventory and several coastal defense batteries after the operation. These assets include Iranian-produced Badr-F tactical missiles with 160-kilometer ranges and a limited number of anti-ship cruise missiles modified for land attack. Dispersal to mountainous hide sites and urban areas complicates targeting efforts while maintaining retaliatory capabilities. U.S. Navy initiatives aim to counter these threats through next-generation strike systems. The Conventional Prompt Strike program accelerates development of hypersonic missiles capable of hitting mobile targets within minutes. Early testing confirmed Mach 5+ velocities and maneuvering capabilities superior to current SM-6 performance. Engagement timelines are reduced from 30 minutes to under 7 for time-sensitive targets, critical against Houthi tactics. Warhead designs emphasize minimized collateral damage for urban engagements, ensuring precision in densely populated areas. Houthi adaptation efforts challenge conventional countermeasures. Post-strike surveillance revealed modified supply chains using civilian trucks with concealed compartments. Rebel technicians can reconstitute launch teams within 72 hours of strikes, faster than historical recovery rates. Iranian technical support remains a concern. Intercepted communications referenced possible GPS spoofing systems to counter U.S. precision munitions. These developments necessitate constant intelligence updates to maintain tactical advantage. Regional partnerships are vital for sustained deterrence. Saudi Arabia's border surveillance networks provide early warning of missile movements, while Omani coastal radar stations monitor maritime smuggling routes. The Combined Maritime Forces Initiative expanded patrols in the Arabian Sea, though Persian Gulf allies remain reluctant to directly confront Iranian supply vessels. These alliances form layered detection zones complementary to U.S. ISR platforms, but require delicate diplomatic maintenance. Ongoing operations reflect an adjusted strategic posture favoring proactive engagement. CENTCOM revised rules of engagement to permit strikes on missile transport vehicles preemptively, a shift from previous reaction-only protocols. FA-18E squadrons began carrying AGM-158CL RASM anti-ship missiles during patrols, providing instant response options against maritime threats. These measures aim to disrupt the Houthi supply chain, rather than intercept launched missiles. Technological solutions address specific battlefield challenges. The Marine Corps deployed ground-based air defense systems to Yemen's periphery, supplementing Saudi Patriot batteries. These ANTPS-80 radars significantly improve low-altitude detection against cruise missile threats. Meanwhile, Space Force tracking satellites enhance coverage of suspected Iranian arms shipments, though cloud cover and deception tactics limit effectiveness during critical periods. Iranian responses remain strategically cautious but tactically adaptive. No overt resupply convoys were detected in the 30-day post-strike window, reflecting concerns about secondary U.S. interdiction. However, commercial satellite imagery showed increased activity at Keshem Island storage facilities, a known transshipment point for Yemen-bound arms. Tehran also accelerated training for Houthi operators on newer Corded-3 air defense systems, though none were yet confirmed deployed in Yemen. The operational tempo reveals systemic limitations on both sides. U.S. strike planners face difficult choices balancing immediate threat suppression with preserving intelligence-gathering opportunities. Houthi forces struggle with maintaining missile reliability amid supply shortages. Post-strike assessments noted a 40% increase in failed launch attempts. These constraints shape an evolving stalemate, where neither side can achieve decisive advantage. Future conflict dynamics will likely emphasize electronic warfare and deception. Pentagon budget documents reveal increased funding for EA-18G Growler squadrons, specializing in Middle Eastern threat profiles. Concurrently, Houthi social media channels boasted about acquiring Russian-made Sapphire radar jammers, though authenticity remains unverified. This electronic arms race compounds the challenges of maintaining aerial superiority in contested environments. The Houthi attack on a US F-16 led to a decisive display of American military strength. The operation, from evasive maneuvers to coordinated strikes, highlighted integrated technology and strategic execution. Key actions like the SM-6 and Tomahawk strikes degraded 40% of Houthi missile stockpiles, reinforcing that targeting U.S. assets invites strong retaliation. Despite Iranian support, advanced systems like hypersonic missiles are crucial for future engagements. This conflict underscores modern warfare's complexity, where technology and human expertise converge. Like a phoenix rising, U.S. military resolve remains unyielding, ready to dominate contested battle spaces against adaptive adversaries.